Welcome friends, Igor is here, and in this video we will discover connections between invertible matrices and invertible linear transformations. In this lesson we will prove that a linear transformation is invertible if and only if its matrix representation is invertible as a matrix. Observe that the matrix representation of an inverse linear transformation is an inverse of the matrix representation of the original linear transformation. And we will learn how to use matrix inverses to check that a linear transformation is invertible and compute its inverse. Let's get started. Suppose that we have a linear transformation T that goes from a vector space U to a vector space V. We fix any basis B for the vector space U and any basis C for the vector space V. This allows us to construct the matrix representation of the linear transformation T relative to these two bases, and it turns out that the linear transformation T is invertible as a linear transformation if and only if its matrix representation is invertible as a matrix. Moreover, when T is invertible, the matrix representation of the linear transformation inverse of T is the matrix inverse of the matrix representation of the original linear transformation T. For the proof of this result, let's list the vectors that comprise bases B and C respectively. Notice that these two bases have the same size because for T to have a chance to be invertible, the vector spaces U and V must have the same dimension. The theorem involves an if and only if statement. This means there are two implications for us to establish. In the forward direction, we are going to suppose that T is an invertible linear transformation. This assumption means that there exists an inverse linear transformation, T inverse, that goes from the vector space V to the vector space U. Let's look at the matrix representation of the linear transformation T relative to the bases B and C, and the matrix representation of the linear transformation T inverse relative to the bases C and B now. Let's see what happens when we multiply these two matrices. In one of the previous videos we proved that multiplying matrix representations corresponds to composing their linear transformations. But the composition of T with T inverse is the identity linear transformation on the vector space U. It now remains to figure out what the matrix representation of the identity linear transformation is relative to the bases B and B. It is defined column by column, and each column is computed as follows. We take one vector from the basis B of the domain, then we apply the linear transformation to this vector, and then we coordinatize the result relative to the basis of the codomain, which is still the basis B. Well, the identity transformation does not change the input, and now we have to coordinatize the vectors of the basis B relative to the basis B. We have discussed this when we defined vector representations, and the result of this coordinatization is the standard unit vectors. Now, what kind of matrix has standard unit vectors as its columns? It is the identity matrix. Next, let's multiply these two same matrices but in the opposite order. We will go through a similar computation. This matrix product is the matrix representation of the composition of linear transformations. But now first we apply T inverse, then we apply T. This composition is the identity linear transformation on the vector space V. To compute this matrix representation, we use its definition. The identity transformation does not change the inputs, and when you coordinatize the vectors in the basis C relative to the basis C, you will get standard unit vectors, and the matrix whose columns are standard unit vectors is the identity matrix. The two matrix representations multiply each other to the identity matrix. Therefore, these matrices are invertible and they are inverses of each other. In particular, we have proved that if T is an invertible linear transformation, then its matrix representation is an invertible matrix, and its inverse is the matrix representation of the linear transformation T inverse. In the opposite direction, let's assume that the matrix representation of T is an invertible matrix. Therefore, it is also non-singular. Let's compute the nullity of the linear transformation T. By definition, this is the dimension of the kernel of T. In one of the previous videos, we have proved that the kernel of T is isomorphic to the null space of its matrix representation, and isomorphic vector spaces have the same dimension. But the dimension of the null space of the matrix is the nullity of this matrix. And we know well that the nullity of a non-singular matrix is equal to 0. This shows that the dimension of the kernel of T is equal to 0. Therefore, the kernel of T is trivial, and this means that the linear transformation T is injective. Next, let's compute the rank of the linear transformation T, which is defined to be the dimension of the range of T. In the previous video, we have proved that the range of T is isomorphic to the column space of its matrix representation. In particular, these vector spaces have the same dimension. But the dimension of the column space of a matrix is its rank. And the rank of a non-singular matrix is always maximum possible. It is equal to the size of the matrix. In this case, it is n, which is the same as the dimension of the vector space V. This computation shows that the dimension of the range of T is equal to the dimension of the codomain of T, vector space V. Also, range of T is a subspace of V. When they have the same dimension, it means that range of T must be equal to all of V. This tells us that the linear transformation T is surjective. So, T is both injective and surjective, therefore it is invertible as a linear transformation. And we have proved the opposite implication. If the matrix representation is invertible as a matrix, then the linear transformation is invertible as a linear transformation. This completes the proof of the if and only if statement. Let's see this result in action. We have this linear transformation T from the vector space of polynomials of degree at most 3 into the vector space of 2 by 2 matrices. As always, we fix nice bases B of polynomials and C of matrices, and we construct the matrix representation of this linear transformation T relative to these two bases. I will not go through the column-by-column computation of this matrix representation. Please pause the video for a minute and make sure that you can reconstruct this matrix. Now, I'm going to explain how we can use this matrix representation to first of all decide if T is an invertible linear transformation, and secondly, if T is invertible, compute the inverse of T. For this, we simply check if this matrix representation is invertible as a matrix, and we know how to do this. Moreover, this kind of computation automatically computes the inverse of a matrix when it is invertible. We have discussed how to do this in the previous video, but let me quickly remind you how to do this. We construct a bigger matrix where the left part is the original matrix and the right part is the identity matrix. Then we reduce this big matrix, and if the original matrix reduces to the identity matrix, it means it is invertible, and the right part in the reduced matrix is the inverse. Now, because the matrix representation of T is invertible as a matrix, it tells you that T is invertible as a linear transformation. Moreover, the matrix representation of the inverse of T is given as a matrix inverse of the matrix representation of T. And our computation on this slide in reducing the big matrix tells us what the matrix inverse of the original matrix is. So, we know the matrix representation of the linear transformation T inverse. Now we can use this matrix representation to reconstruct the formula for T inverse. T inverse is a linear transformation that goes from matrices to polynomials. So let's feed T inverse an input matrix. Then we apply the fundamental theorem of matrix representation. To apply a linear transformation is the same as first coordinatize the vector in the domain, then multiply by the matrix representation, and then uncoordinatize the result in the codomain. We chose a nice basis C for the space of 2 by 2 matrices, so it is easy to coordinatize any matrix. Also, we just computed the matrix representation of T inverse. Now we perform this matrix vector product. Now we compute the result of this matrix vector product. And the last step is to uncoordinatize this column vector relative to the basis B, which is a basis in the vector space of polynomials. This computation gives us a formula for T inverse. It tells you what T inverse does to any 2 by 2 matrix, and it gives its value as a polynomial of degree 3. Let's apply this general result in a particular case of linear transformations from column vectors to column vectors. We know that any such linear transformation is defined as a matrix multiplication. So suppose we have a square matrix A of size n, and we define a linear transformation T from Cn to Cn as multiplication by this fixed matrix A. Then A is an invertible matrix if and only if this linear transformation T is an invertible linear transformation. Before I show you the details of the proof, here's a quick idea why it works. This matrix A is in fact a matrix representation of this linear transformation T relative to very specific bases, standard unit vectors in both domain and codomain. We have discussed this previously, but now I'm going to quickly remind you why it works this way. So, for both domain and codomain, we're going to choose the bases B and C, which consist of standard unit vectors in Cn. Let's construct the matrix representation of the linear transformation T relative to these bases. The ith column of this matrix is the value of row C on the linear transformation T applied to the ith vector in the basis B, which is simply the ith standard unit vector. To apply linear transformation T is the same as to multiply by the matrix A. And the product of a matrix and the ith standard unit vector is equal to column number I of that matrix. And all that remains to recall is that coordinatizing a column vector relative to the standard unit vectors is just the column vector itself. In other words, coordinatizing relative to standard unit vectors is the identity linear transformation. This shows that column number I of the matrix representation is equal to column number I of the matrix A. This holds for all columns. Therefore, the matrix representation of T relative to these bases B and C is equal to the given matrix A. And now all we have to do is to apply our big and powerful hammer. A linear transformation is invertible if and only if its matrix representation is invertible. But we just showed that the matrix representation is this matrix A. Therefore, this linear transformation T is invertible if and only if the matrix A is invertible. Guess what? This means we can extend our old list of equivalences for non-singular matrices by one more entry. Square matrix A is non-singular if and only if the linear transformation defined as multiplication by this matrix is an invertible linear transformation. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will discuss what happens when you change a basis of a vector space. I will see you later.